So our webinar is gonna start soon, and we're waiting for more people to join.
All right, so we're gonna start today's webinar. All right, hi everyone. This is Lord Math Contest Club. I'm Garrison.
I'm Melanie, and we are the hosts for today's webinar. And we hope our events can inspire more people's interest in math and also give us study tips. Our webinar is going to be around 1 hour, and today we're pleased to invite two professors from the Math Department of UBC to give us ideas about what mathematicians do in their daily life.
First, we'll have Dr. Brian Wetton, whose original background is in numerical analysis. He has now become more motivated by industrial applications and has developed a skill in mathematical modeling. He is going to give out some concepts and share his deep understanding of math. Unfortunately, he can't be here today, but he made the video for us.
Hello, my name is Brian Wetton. I'm a professor at the University of British Columbia in the mathematics department. I was asked to give a short presentation by the president of your club, Garrison Chu. I apologize for not being there in person at your event. Oh, you can see I'm at home. I'm getting ready to go on a research trip to Michigan State University. I have a close colleague there that I work on. I worked on several projects with him. And the latest thing we've been looking at are models of sea ice formation. These are sort of detailed models of the sort of microstructure of sea ice formation, but some of the models could be used as part of climate change models because sea ice is important to the prediction of long-term climate change. Previous work from last summer with the same colleague was published in the Society of Industrial and Applied Mathematics Mathematics journal. And maybe this is a good time to just start talking about a third of my job is mathematical research. So University of British Columbia is a research university. It consistently ranks in the top 40 research math departments in the world. So that's quite a nice place for me to be at. So I do research work, as you can probably understand from the project I was talking about in applied mathematics. That's about a third of our department, as you could consider applied mathematicians. which is a higher ratio than most departments. We have a strong applied math group. And of course, the rest are doing more pure mathematics. So my research work involves a mix of differential equations, linear algebra, scientific computing, and I have a background in physics that helps. And I've worked on problems from material science, so understanding microstructure. That's part of the background that's helping me with the sea ice modeling. And I've also worked on electrochemical systems, fluid dynamics, and other applications. So again, that's about a third of the time in my job. The other third of my time is teaching. Typical for research universities, our teaching load is 3 semester courses a year. And I teach everything. And in fact, next year, I'm teaching everything from first year calculus to graduate level material. Some of the material I like teaching the best are our senior courses in differential equations and scientific computing. I've got one of those next year as well that I'm looking forward to. I'm actually working on writing a set of lecture notes, maybe an open source textbook in that material that combines the modeling, the analysis, insight, and the scientific computing, along with some useful applied mathematics techniques like asymptotic analysis. Because Garrison asked me to talk a little bit about what a day in my life is like. So there's a third of my work time left, and that's administration, which I guess you have in every job. There's committees. I spend time applying for research grants to be able to do this travel that I'm coming up. I review research papers. I'm an editor, in fact, on the journal I mentioned earlier. Of course, this seems like a pretty nice job. You get to pick what you work on, and it's exciting. I think the audience out there, the students, are interested in mathematics, and so they pay me to do that roughly 2/3 of the time. Of course, you have to have some mathematical skill beyond the ordinary to get a research professor job. But you also need more than that. The comparison I like to make is to professional musicians. You can be a very good professional musician, but are you an international level musician? Part of that skill, but part of that is just the right opportunities have to come up. You have to be mentored. You have to have some commercial contact. This is for musicians, right? Come at just the right time. And certainly the mentorship part is necessary. And you also have to find the passion for mathematical research that you need to be able to make it through a graduate degree and beyond. And however much you like math, you may not find that. So, of course, I recommend it as a career, but I also wanted to point out there is many other career opportunities that you can get with a mathematics degree, an undergraduate mathematics degree. And maybe for the parents in the audience, if there are any, I guess I want to stress that this is a degree that leads to excellent career opportunities. There's all kinds of things in math, finance, actuary. It's also a good first degree for education, MBA, law, and many other degrees. And I can say, even if you don't take a mathematics degree, but take some more math courses beyond what you need because of interest or math minor, which is something that you can take at many Canadian universities. Those skills will be useful in your profession. In your group, for whom you may be the person that knows the most mathematics and has the most insight into questions that come up of a sort of technical or theoretical level. You may be able to put them in the right framework to find basically easy solutions to some problems if you happen to know the right mathematics. And even if you don't, if you know enough mathematics to know the kind of question it is, then you can seek the right kind of professional help to help you out. And if you know no mathematics, then your whole group is sitting there not knowing how to make progress on those questions. If you are planning to go to a mathematics degree at your next education stage, do think of taking maybe a little bit more computer science and statistics courses than you are obligated to take for the degree. Those will be a big help in your profession. Actually, even if you're not taking a math degree, basically anything these days, those skills will be useful. I guess I wanted to make one final point. Again, not for students that are going off to university this year, because I'm sure those decisions have already been made. But for students that are thinking of going to university, who are now finishing or finished grade 11 or earlier grades, I have to say this is something that many people don't realize, that any major Canadian university will provide an excellent education in mathematics or any other discipline. So I'm actually a graduate from the University of Victoria. I'm from British Columbia originally. And I went off to New York University to do my graduate work. And I was as well trained or better than most of the American students and most of the international students. So a small place like Yeager trained me very well. And they'll do the same for you. Now, I guess the one exception is if there's a particular program at a university that you want, that's only offered there, or if there's some kind of an international reputation that you need to get into. But other than that, I would say UBC, UVic, SFU in British Columbia, UNBC, and similar universities across Canada will all provide an excellent education. I guess I was a little vague on actually what you wanted for my presentation, but I hope this gives you a sort of sense of what my career has been like and what some options for students interested in mathematical careers, what they might be. And if you had any questions, Garrison has my email address, so just ask him for it and I'd be happy to answer. Good luck with your event, and again, sorry I could not be there in person.
Okay. Lots of appreciation for Dr. Wetton. As he said in the end of the talk, if you have any questions for Dr. Wetton, please ask in the chat box.
So now we're going to the second professor. Dr. Elyse Yeager graduated in 2015 with a PhD in mathematics and a Master of Science in the teaching of math. So now let's welcome Dr. Yeager to present about a day in her life and her hobbies.
My name is Elyse Yeager. I'm an associate professor of teaching with the math department at the University of British Columbia. Howard asked me to give a talk about a day in the life of a mathematician. When you spend a lot of time thinking about math, you practice thinking in very specific ways. And sometimes those ways of thinking can bleed over into the parts of your life that aren't explicitly mathematical. So I thought I would share an anecdote about some of my hobbies, which on the surface should have nothing to do with mathematics, and the way that my interactions with them are impacted by the fact that I think about math quite a lot. Hobby number one is doodling knots. When I was in high school, I got really fascinated by this type of decorative knot work. And I learned a pretty straightforward way of drawing these knots myself. This is relevant to the anecdote and kind of fun. So I'm going to quickly explain the idea behind how we can draw these ourselves. The first thing to notice here on the left, where we have this very plain basket weave, is all of the crossings happen at these very regular intervals. Not all knots are like this, but the kind we'll be drawing will be like this. On the right-hand side, it's similar, but we don't have an actual crossing of two strands at each of these points on our grid. Sometimes we have two strands that don't cross. If I want to draw them on my own, I'm going to start with a grid like this. And the idea is as follows. The strands of the knot want to move diagonally between these red dots. So if I don't have anything else going on, I start anywhere. If I'm here, okay, my strand wants to move diagonally. So it'll go like this. And then it continues to want to move diagonally and so on. And it goes in both directions. So in this example, we don't have anything to stop them. So every strand just moves diagonally to the dot nearest to it. And then to make it look like a knot that would be physically made out of something, we put in our crossings as just alternating over and under. So our plain knot would look something like this. Okay, let's make it more interesting. What if I block one of these crossings? So I'm just going to put a bar there. Now I'm going to say they're not allowed to cross, but I'm still going to think of the strand as wanting to tend towards the next dot. So if I'm this strand going in this direction, I would like to tend towards here, but it's blocked. So what happens is it gets deflected. Just imagine like you're on a walk and you want to go here, but there's a wall, and so you have to turn. And then the same thing is going to happen down here. If my strand is here moving up, it would like to move to the next dot. It can't because there's a wall there. So it gets deflected down. So that's how we can put some more interesting features into our knot. So just to practice, let's do one. I like to close off the edges. It looks a little bit weird if the strands go off into the margins. So I'll just put lines through all of those dots, and then I'll just add a few other lines. So maybe I'll add a line like this and like that, and like that, and like that. Make it have a bit of rotational symmetry. All right, something we like to think about in mathematics that suddenly pops into your head when you're not doing mathematics. Okay, so according to the rules, I'll start anywhere. Let's say here, and let's say I'm going down. Okay, I would always like to go to the next dot. So there's no problem here because it's not blocked. But when I try to go to the next dot, it's blocked. So I get deflected and I come here, no problem to the next dot. But at this point, I would like to move to this dot, but it's blocked. So I get deflected. I would like to move to this dot, but it's blocked. So I get deflected. I would like to move to this dot, but it's blocked. So I get deflected. Deflected, no problem. Deflected, no problem, deflected, deflected. Now here, I would like to go to this dot, but it's got a block, so I get deflected. And then I would, as a second resort, I would like to go here, but that's also blocked, so I get deflected again. And so we get this corner piece like this. Okay, and I'll just finish this out. And now to add the final touches, I just make the strands look like they're going over and under each other. So there's hobby number 1. Now, when I learned this in high school, I don't think I thought of it as particularly mathematical, but now that I've done more math, I actually do, because it's very algorithmic, right? An algorithm is a list of steps for doing something, and that's something we do a ton of in mathematics. When you learned long division, for example, you were learning an algorithm, and there's a whole genre of art called algorithmic design or generative art, where you take a computer program and you feed it some rules, so some algorithm, usually seed it with some kind of randomness, and then those rules get turned into a picture. Okay, so how is this mathy? It's very algorithmic. Hobby number 2 is crochet. Something that I quite enjoy with crochet is taking an interesting visual image and figuring out how to make it in crochet. If we were just drawing, we can put a mark wherever we want on the page, but there are physical limitations to what you can do with a craft like crochet, and so it takes a little bit of engineering to figure out how to translate marks on a page into something that you can make within these physical limitations. So this isn't a visual design that I came up with. It's called a pursuit curve, but I thought it was nice and figured out how to make it in crochet. So what are the physical limitations? Well, there are only certain shapes that we'll say are easy to make. You can certainly do things that are harder, but for the sake of this talk, we'll say that there are a few shapes that are easy to make. We can do straight lines and right angles, so we can make rectangles and squares, or like an L if we wanted. Hexagons are pretty straightforward, but actually not relevant to the talk. And we can do pieces of circles, right? So a circle is pretty easy to make, but I could also do a semicircular arc, right? Something that looked like a piece of a circle. So hobby number 1, hobby number 2, it occurred to me that it would be fun to figure out if I could make these types of knots in crochet. This is where we start getting into something that feels more traditionally mathematical. What are the shapes I can do easily? Straight lines, right angles, parts of circles. So I wanted to find a way to break all of the pieces here into those components. So for example, I could call this a quarter of a circle, and then a big straight line, and a quarter of a circle, and a big straight line, and so on. Here's a big straight line. Here's a big straight line. The corners get a little bit more complicated, but here's what I can do. That right there can look like a right angle. And then this can look like an eighth of a circle. So I can take an eighth of a circle, a right angle, and an eighth of a circle. In order to figure out exactly how many stitches to have and where to put them, there's a lot of geometry, but it's just high school geometry, the stuff that you've probably learned. I would need to know the radius of this part of the circle. I would need to know how many degrees or radians are being traced out. In this example, say an eighth of a circle. And it gets pretty tedious if you wanted to do a thing of any size, because you have to do quite a lot of these. But it really is just high school geometry. Okay, so that's mathiness number 2, is we have the geometry of it. We have a very computational problem now, where I want to be figuring out what's the radius, what's the arc length, what's the angle of all of these geometric shapes. Okay, so here are the shapes that we saw in the other piece. This is where, in my opinion, this project got the most mathy of all. When you're studying mathematics, I said that you think in very particular ways. When we make mathematical statements, we want to make sure that we've considered every possibility so that statement is 100% true all of the time. I want to depart from this real fast just to give you a more concrete example of what I mean. Here's a statement you're probably familiar with. If you're doing some computations and you want to cancel and you have the same thing on the top and the bottom, you can cancel them out. Most of the time, this is what people think of. This is the tool that people think of. But if you're a mathematician, you have to be very careful to say, this doesn't work 100% of the time. For example, it only works if I'm not dividing by 0, right? Otherwise, I can't necessarily do this cancellation. And the more mathematics you do, the more you get accustomed to really interrogating your statements and saying, is my statement true 100% of the time? Okay, so what happened to me when I was doing this project? Well, I figured out that for simple knots like this, okay, I could break everything up into a finite number of components. We have half circles, these corners, which are circle, straight, circle, right angle, circle, straight lines. But was that everything? Using this very algorithmic way of generating these knot designs, what are every single component that could possibly come up? And this is where I feel like, again, the mathematician in me really took over. I couldn't rest until I had answered this question for myself. I don't mean that in a bad way. It was a really fun project to do. But if I had stopped studying mathematics, say after my bachelor's degree, I don't think this ever would have occurred to me. And if it occurred to me, it definitely wouldn't have bothered me to leave it hanging in the wind. So here's the sub-project. I want to classify actually all of them. And then, okay, see if I can crochet them. If I can, then any type of knot you can make with this algorithm, in theory, I can write a crochet pattern for. So we want an exhaustive list. I want to be 100% sure that I have categorized, classified every single shape that could happen. So how can we be sure we've gotten them all? All right, in order to be sure that we've gotten them all, we're going to break up our algorithm for drawing these knots into very small steps. So every segment starts and ends at a dot. So I'm going to call that a segment, from a dot to a dot. And what can happen at a dot? Maybe there's no bar and my strand just goes straight there. Or maybe there is a bar and those bars can be horizontal or vertical. We don't have diagonal bars. Okay. At a crossing, we have two strands and they go in 4 directions. If it's an actual crossing, so there's no bar. So let's consider everything that could happen at a crossing. Now, there's some magic words that are going to make our life a lot easier. Those magic words are without loss of generality. So there's actually 4 cases to consider. This case, that case, that case, that case. At any dot where 2 strands cross, there's 4 places that they could go. But if I'm considering this, I can just rotate it 90 degrees and get this. And I can just rotate that 90 degrees to get this and rotate that 90 degrees to get this. So if I only consider one case, say I only consider this case, I'm going to still get every shape, just maybe rotated. So instead of considering 4 shapes, I'm going to convince myself it's allowed to only consider one shape and understand that in order to really get everything, I might later have to rotate it around. But if I have a physical object, I mean, this physical object is the same as that physical object, so rotation doesn't bother me too much. Okay, so I'm going to consider what happens when I started a crossing and my strand is going up and to the right. This is where our 3 options first come in. I'm going up and to the right. I would like to hit this dot, but there are 3 things that could happen, and only 3 things. There could be no wall, a horizontal wall, or a vertical wall. So let's take all 3 of those options. Okay, if there's no line here, I'm done. I go from dot to dot, and I'm finished. What if there's a horizontal line? If there's a horizontal line, I'm going to get deflected, and I'm going to start going towards the next red dot, which is going to be approximately here. So I'm not quite done with my segment. If there's a vertical line, same thing. I start going here. I'm going to be deflected in a different way. I'm going to be deflected here, moving towards the next dot, which is going to be there. These are the same shape. They're just rotated. So once again, I'm going to say, if I consider this and I consider that, I'm going to get the same list of shapes just rotated. So in order to make my life a little bit easier, I'm just going to consider that shape. Okay, so I found one shape, straight line. We already knew about that one. Now let's consider what happens if we don't have a straight line. Okay, I'm deflecting towards this dot. And again, there are 3 options. Maybe there's no line. Maybe there's a horizontal line. And maybe there's a vertical line. But those really are the only 3 options. So as long as I explore all 3 of them, I'm not accidentally missing any potential shapes. Okay, if there's no line, I just head towards that dot and I'm finished. My segment is finished, and this is a quarter of a circle. What if there's a horizontal line or a vertical line? Well, if there's a line, I get deflected again and I'm not done. I have a different shape. If there's a horizontal line, I get deflected up. If there's a vertical line, I get deflected down. So now these are no longer the same shape. I can no longer say without loss of generality, I'm only considering one. I have to consider both of them. And because I have not yet ended at a dot, my segment, which goes from dot to dot, is not yet done. So on the left, I'm heading towards a dot that's up here. On the right, I'm heading towards a dot that's down here. And I have to consider both of these cases to make sure that I'm not accidentally missing any shapes. Okay, so one case was where we had that horizontal bar. The other case was where we had that vertical bar. In both cases, I call the dot we're heading to D. D might have no bar, it might have a horizontal bar or a vertical bar. D might have no bar, it might have a horizontal bar, it might have a vertical bar. So our cases are proliferating. We have to be very careful in how we think about this to make sure that we're not missing any. And this is another mathematical skill, to take a big problem, break it into a million tiny pieces and not get lost, and make sure that you're not dropping any of those pieces by the wayside. It's a cognitive skill, and it takes practice in the same way that running for a long time without stopping also takes practice. Okay, so undeterred, we carry on. Let's start up here. Now, if I don't have a bar, I'm done because my strand reaches its goal. And just aesthetically, I'm not going to make it do really big curves. I'm just going to have it go up and then pretty straight and then up. Okay, so that's one case that's finished. And this is now the first shape that we didn't have before. So we found something we didn't know about before. Okay, now let's look at this shape down here. This is the other one where I don't have a bar, which means this is the other case where I get to be done. So what happens here? Okay, I start at A, I want to go to B, it gets deflected. I want to go to C, it gets deflected. I end up at D. This is a shape we saw before. This is what we were drawing as this corner. And again, for aesthetic reasons, I liked to put an angle there. This is where it becomes less mathematical. Of course, you could have made it curved if you wanted. Within our setup, there's no reason why it couldn't be that way. Okay, so that's another segment. So we knew about that one, but this one was news to us. All right, now I've got these ones left. I want to look at this one. So if D has a horizontal line, my strand is going to be deflected, but it's not going to be deflected somewhere new. It's going to be deflected towards this dot, which we've already dealt with. It starts at A, wants to go to B, gets deflected, wants to go to C, gets deflected, wants to go to D, gets deflected, and then it can't be deflected at A because A can't have a bar, because if A had a bar, we wouldn't have started there. So now we have another shape that we didn't have before. And there's some artistic choices to be made at this step. We know that this is roughly the path that our strand needs to take, but we can decide what we want it to look like. Maybe we want it to look a little bit square, maybe we want it to look more like a circle. That's an artistic decision, but we found one more component, one more way that a segment can look that we didn't know about before. So I want to detour now. Now we found 5 shapes. We knew about these 3 before. We also found these 2, and we know that there are more because these 3 cases haven't been dealt with yet. So there are going to be more shapes coming. At this point, I'm actually going to sort of stop the proof. The purpose of this talk is not to prove this result. The purpose of this talk is to talk about the kind of thinking that goes into this result. At this point, it gets technical and honestly a little bit boring. So I'm just not going to bother. But I want you to imagine that we can finish out this, it's called a case analysis, or this like tree of what is every possibility. We can finish out this thought process using pretty much the same type of thoughts that we've used so far. And we can come up with a complete list of every single type of component that there could possibly be. I think there's about 4 more that we haven't found yet. So for this project, again, I want to point out 3 sort of areas where it was quite mathy. One is that drawing these knots is very algorithmic, and that's mathy, but in a way that a lot of people have access to, not a way that you really need to study a lot of mathematics for. The second way was this computational geometry. So in order to make this physical object out of crochet, and this is a picture of a physical object, I had to figure out, okay, if from here to here is a quarter of a circle, how many stitches are here and how many stitches are here and how many stitches are here, and that's just the arc length. So there was a lot of computation. That's a type of mathiness that you have access to now at this point in your education, right? From your geometry classes. There's a lot of it, it's a bit tedious, but you have access to it. The third part was me deciding that I absolutely needed to know what every single possible component was that could arise. So here was one of those components that we found in the case analysis that we didn't necessarily see when we were starting with those easy examples, this sort of twist that goes on over itself. And then once you have all of these components, like I said, I was confident that I could make an arbitrarily complicated knot. Any knot that I could draw using this algorithm, I could in theory make in crochet. It takes a while, and at some point I got a bit bored and stopped, but I was pretty pleased with the results. So that is my example of a day in the life of a mathematician, where the ways in which I think when I'm doing mathematics start popping up, even when I'm doing projects that are not explicitly about mathematics.
All right. And again, a big thank you to these two wonderful professors and their inspiring talks. Now we're heading to the end of our webinar. If you have any questions for professors or me and Melanie about math and contests, please feel free to ask. We'll resume our weekly meetings this week, every Tuesday and Thursday at lunch in A301.
So I would like to ask any questions. You can type in the chat box. Why? Oh wait, why did the professors pursue math? Whoa. Probably we should like have an email to ask those professors.
Professors are generally okay with people sitting in on lectures that they did not sign up for. Well, great question. I'm gonna ask him. Thank you, Justin Wong.
Great content, yeah. I do agree, great content. So any other questions? Is graduate school tough? Oh. Well, I'm sure it's not that hard for you, Eleanor.
What's your path for becoming a professor after undergraduate studies? Does university have
Okay.
content?
Well, I'm not quite sure whether university have math contests or no, but I assume yes, because I've seen like news in MIT's math department website. Yeah, exactly, math Olympiad. So
What's the difference between pure math major and a pizza? A pizza can feed a family of 4.
wait, any other questions?
Yeah, being a professor is an honorable job. I agree with Paula. Have you experienced discrimination in your field as a female mathematician? Yeah.
Probably will email the professors too. Yeah, we do agree math is basic. Well, so any other questions, or we can like actually end our webinar today?
What are some expectations versus reality as a math professor?
Okay, for now, I think it's the end of our webinar. And thanks for coming, and see you all soon. Bye. Thank you.
Thank you, everyone.